Hey, okay. No, get out of the picture. Jeepers. This is live. This is professional. Okay, here we go. Hopefully, mostly we're just going to be solving the tangent problem. So you've looked at a few of the techniques of calculus where you're doing things like finding out the value of pi or the area of a circle. Really, what we do in this course mostly is we're dealing with the tangent problem, which has to do with finding the slope of a tangent to a curve at a point. Okay, so here we go. I have drawn a curve right here. And as you can see, this is a secant because it cuts the curve in two places. And we can find the slope of that secant fairly easily. It's just delta y over delta x, right? Which we learned back in grade 9. That was the easy way to do it. Rise over run. This is point 1 with coordinates x1, y1, and this is point 2 with coordinates x2, y2. So we put the little subscripts in there just to add more symbols to make it more complicated. So delta y, we calculate by going y2 minus y1, and delta x we do by x2 minus x1. So we've managed to make this simple thing a little bit more complicated just by using subscripts and things like that. Still just the slope calculation. Okay, now we're going to add another layer of symbols to this. So we're actually going to show y2 being calculated as a function of x. Yeah, so we're going to call this f at x1, and we're going to call this f at x2. Okay, so those are just the y coordinates. So now we can change this up again. So y2 is f at x2, and y1 is f at x1, and this is x2 minus x1. Okay, we're gradually headed for this thing we call the difference quotient, which later on turns into the derivative. Okay, instead of x2, to do this conveniently, what we're going to do is we're just going to have well, actually, let's call this a for now. So this has the coordinates a and f at a. And we are going to go over h. Okay. And so this is no longer x2 and f at x2. Oh my goodness, I'm going to have little blank tips on my fingers, but that's okay. So this is going to be this is going to be x plus h, and the y coordinate is going to be f at x plus h. This is still the same thing. We're okay with that? So this is just h. That's my run. That's my change in x. And now we're going to go to the final form of the difference quotient. Everybody ready for it? Instead of x2, now I've got x plus h. Instead of y2, I've got x plus h. Instead of y1, I've got f at, and I was calling this a, f at a. And then x2 minus x1 is really just h. Okay, so this becomes the difference quotient. This is the slope of a secant between this point a, f at a, and some point over here a little bit, a plus h, and f at a plus h. All right, does that seem okay? Okay so far? Difference quotient. Write it down. Super important. Now this is the slope of a secant. And the slope of a secant is pretty easy to calculate. We want the slope of a tangent. And we want the slope of the tangent right there at this point A. Okay? We do that in calculus by looking at the slope of the secant. As the secant, this h value gets closer and closer to 0. As you can see, we can't actually calculate it when h is 0 because we can't divide stuff by 0. It's just wrong. I think it's in the Bible. You can't do it. Okay. So I'm going to make my function. We are going to find the slope of the tangent to that function at a particular place using calculus techniques of taking a limit. Okay, so here's my function. At least I think this is my function. F at x equals 1/3 x cubed plus x. Okay. And here's our problem. We want to find the tangent slope to that curve. When x is equal to 1. So we're going to be using 1 as our point, and we are going to find the slope of the tangent to the curve by seeing what happens to the slope of the secant as h gets smaller and smaller. Okay? So we're going to keep track of h over here, and we're going to keep track of the slope of the secant over here. And we're going to choose some values of h that are getting smaller and smaller and smaller so that we can shrink this secant down so that it's getting to look more and more like a tangent. Okay? So we're going to go h is 1, h is 0.1, h is 0.01, and we're going to see what happens to the slope of our secant as we plug those things, those numbers in. Okay? So here we go. So the first one, here's our slope calculation. 1 plus h minus f at 1. We're going to do it when h is equal to 1, and we're going to see what our slope of the secant turns out to be just by plugging it into our difference quotient. I have most conveniently just calculated these, so I'm just putting, I'm going to put a 2 in. So when h is 1, I'm going to erase this. My slope's going to be f at 2 minus f at 1, and it's going to be over 1. So it's going to be super easy to calculate. Good so far? Making sense? H is 1, x is 1. We're going to calculate f at 2. We're going to subtract f at 1. That's going to give us our rise, and then we're going to divide by our run, which is just 1. So the function is 1/3 x cubed plus x. All right. Okay. So this actually calculates to 3.3. So if you plug these numbers in, divide by 1, you get 3.3 for your slope. When h is 1. Okay? So we're going to take it closer. We're going to shrink h down a little bit. So instead of 1, we're going to use h as being 0.1. So now instead of f at 2, it's f at 1 plus h. So it's going to be f at 1.1 minus f at 1 divided by 1. Okay? So I'm going to be plugging So I'm going to plug 1.1 into my function for x here. I'm going to subtract f at 1. And then I'm not going to be dividing by 1. What am I going to be dividing by instead? 0.1. Okay? And my slope's going to change. It's going to be a little bit different because I've gotten a little bit closer to that point. Okay. And conveniently, this has been calculated for us. this point, the slope is 2.1. So we've gone from 3.3 to 2.1. And what we want to see is, where does this slope, where does the secant slope head? We can't know exactly what the tangent slope is, but we can see what the pattern in the secant slopes is going to do as h gets smaller and smaller. Okay, let's do this one more time. So instead of 0.1, we're going to go to 0.01. So instead of f at 1.1, we're going to do f at 1.01. We're still subtracting f at 1, because that's the point we're interested in. And we're not dividing by 0.1 anymore. We're dividing by 0.01, because this is our new, that's our new run. Okay, so I just plug 1.01 into that. I subtract what I calculated before, divide by 0.01. And in this case, the slope comes out to 2.01. Does anybody notice a pattern starting? Yes. Okay, so using the language of calculus, if we kept on going, we would see that this slope value is just going to get closer and closer and closer to 2. Okay, so we can use this concept of a limit to say, well, we can't calculate the tangent slope, but we know from the limiting value of the secant slope as h goes to 0 that it's going to be 2. Exactly. So we can use that limit notation now. We can rewrite this whole thing. So we can say the limit as h goes to 0 of f at 1 plus h minus f at 1 over h, and it's important to put that limit in, is equal to 2. Okay, so that is how we solve the tangent problem using these calculus techniques of looking at where the value of the secant slopes goes as h gets smaller and smaller. So we can solve that problem. We can figure out what the slope of the tangent is at any point on that function now. Okay. Is that okay? Nobody's looking too suspiciously at me?